Those of y'all at home, please pause the video, copy this down. What's that look like to you? It does look like a shot put. It's not though. It is a cannonball. Very good. This is a cannonball. I am declaring war on the math department. Please. They don't teach math as good as I do. All right, stop. We're recording. He didn't mean that. Anyway, hey, I want to tell you a little story about cannonballs. Back in the older wars, when cannonballs were being stored on like ships and stuff, the primary weapon of ships, they had an issue because they'd have these stockpiles of the cannonballs, but they were at sea where the air was very salty and humid, and it was bad for iron. What would happen is that the piles of iron would form iron oxide. Anybody know what the common name of iron oxide is? Rust, right? And that's it. You don't need to write it. But that's rust. So the good iron cannonballs would get covered in this stuff right here, and it would hurt their integrity. And a rusty cannonball was dangerous to fire because if you put it into the cannon and light it, and it didn't have any integrity, it could blow up right where you are and have the opposite effect of what you were hoping. So they had to go all chemistry on a way to fix the cannonballs. And they found a way to remove the rust. They did it by a single replacement reaction, REDOX, which we're going to cover today. But it turns out that if you mix this compound with a free element, which is different than synthesis and decomposition we did yesterday, at no point in time yesterday did we mix a compound with a free element. But if you mix this rusty cannonball compound with aluminum, free element, that by adding a little bit of mechanical energy to it, you can make a reaction happen. And right there at that spot where you saw the spark, there was a removal of the rust. There was a getting the iron back to its proper state so that it is less dangerous. So each time that we have this happening, there is a single replacement reaction taking place. And somehow in all my years of doing this, I've never caught my pinkies or my thumbs, but I'm getting older, and that was a good one to end on probably. So that is an example of a single replacement reaction to turn iron oxide by mixing it with aluminum, and it would end up yielding, you don't have to write this, pure iron again. So I'm going to show you how you can come up with this, and there's another product there as well, while we study what's called a redox reaction. Now, the most important thing, the thing I stressed yesterday was, can you figure out what type of reaction you're looking at? So we know it's synthesis if it's a free element with a free element. The other way it's synthesis is if it is a compound with water. That was yesterday. Also yesterday was decomposition, where there's only one reactant, right? No plus signs on the left. Today, though, as you can see, we've got this new skeleton where it's a free element reacting with a compound. Now, y'all, these can be reversed. It's addition. So if it's a free element plus a compound, that's the same as a compound plus a free element. But then you can kind of track what's going to happen by looking at that skeleton reaction on the opening slide. Now, you can see there's all this other stuff on the board. We're going to get to all of that, but I'd like to slowly jump into our first example. So write this down. You do not need to copy down that number line. I'll show you the number line at home soon. Let's see how this works. I know it's single replacement. because one of those is a free element and the other one is a compound. That's what makes today relevant. How do we predict the products? Well, open up your ears. Here's how it works. Step one, we're going to identify the general charges of everything. So have your periodic table handy, have your oxidation states, +1, +2, +3, -3, -2, -1, where they go. If you don't have that, look at a shoulder buddy, because you should always have that on every periodic table I give you. Here's what I know. Calcium is generally positive from group 2. Hydrogen is generally positive from group 1. And chlorine is generally negative from group 17. I'm saying generally because the numbers don't matter here. I just need to know if each individual item usually behaves as a cation or an anion. Your opening slide said that when you get into this position, there's two items that want to switch places. And it's the two items with similar charges, general charges, not exact charges. But do you see how the calcium and the hydrogen are both predicted to be positive? To get to the products then, we simply have to switch their locations. Now, you don't have to draw that arrow. I'm showing you what I'm thinking. You can draw it if you want, though. But on the other side, we just need to switch the locations of the H and the Cl. Now, I've used the phrase they want to or they might a couple times because, look here. What happens if you take a copper penny and drop it into water? What happened? What was that? That was the right answer. What was that? It gets wet. Nothing happens. Now, think about this. If we're assuming pennies are made of copper, they're really not. But if we're assuming that they are, copper would be a free element, water would be a compound, single replacement, right? Except nothing happens. I need you to be able to decipher whether or not anything is going to happen here. But the problem is that you don't know this the way you know penny and water. So I've got to give you a way to say, wait, nothing's going to happen, or heck yeah, let's predict those products. So look at your packet. I need you to go to the next page from where we were yesterday. It's the page that looks like this on the packet. It's the very next page from where we finished yesterday. And I want you to look at that big, long list. Now, look here. This is what I'm talking about. I know it looks like this list is broken up into different sections. It's not. I mean, it kind of is, but it's one long list. So from here all the way down, it's a singular list of elements. All right, everybody see it? This is called the activity series. Your opening slide referred to the activity series, and it explained the way that you look at this. I'm reading from your opening slide. You already wrote this. A reaction only happens if the free element, see the free element, is higher on the list, remember it's one big list, than the element that it wants to swap with. So in this example, the calcium would have to be above the hydrogen. Is it? Yeah. It is. And if you can't see it, have somebody near you point to it. All right. Calcium is above hydrogen. Therefore, let's switch them. Now, if you switch them, the hydrogen will now be all by himself. And the calcium will be bonded to chlorine. And there it is. We did the swap. I'm sorry? Buddy, I get there every single time you and I have this conversation. I eventually get there, but I love you. Check what you wrote. Anytime you predict the products, you've got to do this stuff, right? So here we go. Free element is hydrogen diatomic. Yep. Compound, it's ionic. So check the charges. You'll see it's +2, -1. So there will be a crisscross. And there's the products that would really form in nature. Now, we can balance it with a beautiful coefficient right there, which you should always strive to do. And that is half of our analysis. So for single replacement, check the activity series and it will tell you whether the reaction will proceed. Now, because you're sitting in an honors classroom, there is a second part to this analysis that we're going to ask you to do. Look back at your opening slide. Glance back at what you wrote in the dark. The reason that single replacement reactions are also called redox reactions, those are synonyms. We can use both of them, single replacement and redox, is because reduction and oxidation both take place. That's what the word redox is. And you've got the vocab there from the opening slide. It says that oxidation is the losing of electrons. Reduction is the gaining of electrons, which indicates a changing in charge. So have that stuff in front of you. I know that's new vocab for you, but I want you to see the other thing I need you to do to this reaction. Let's do a redox analysis by analyzing what gained electrons and what lost electrons during the process. To do this, I'm going to list the elements the way you would that you were balancing. So I'm going to list calciums, hydrogens, and chlorines. Looks like we're going to balance it. We're not. I mean, we already did, right? Then I'm going to list their charges on each side of the yield. Now, this comes with an interesting situation. Look here. You see calcium right there? See that free element calcium? I've never asked you for the exact charge of a free element. Because anytime we have a free element, we don't look at charges. We just look at Brinkelhoff, right? It either is or it isn't. But to do a redox analysis for the first time ever, I'm going to ask you about the exact charge of a free element. Does anybody know what it is? It's 0. Do you know why they know that? Because it's on the opening screen. Look back at your opening screen, and it says that free elements, all of them, have an oxidation state of 0. So this is a brand new idea for you. So we need it to just soak into your brain. If it is unbonded, its charge is 0 no matter what it is. But the bonded ones follow the rules that you're used to. Hydrogen in group 1 is +1. Chlorine in group 17 is -1. That part doesn't change. Now, let's do the products. Here we go, here we go, here we go. Hey, look at that. Anybody want to take a guess what that hydrogen's charge is? 0, because he is a free element. All free elements have an oxidation state of 0. But a bonded calcium is +2 from group 2, and a bonded chlorine is -1 from group 17. Hey, we know how the charges changed. See how calcium became more positive? You see, over the course of the reaction, he became more positive. If you look at the opening vocab, to become more positive, you have to lose electrons. If you lose electrons, you are oxidized. Calcium was oxidized. Hydrogen went from +1 to 0. He lost some of his positivity. You can only do that by gaining negatives. Hydrogen gained electrons, which the opening slide describes as reduction. He was reduced. And what did chlorine do? He didn't do anything. Yeah, he wasn't oxidized or reduced. In single replacement, there's always going to be one species that's unchanged. And that is all of the skills of the day. There is. It's called Monday. We also call those precipitation reactions, but
Like, if the charges have changed, do we have to write that?
You don't. I mean, really, writing this workout's not going to be asked. You're going to run into a question that just might say, what species was unchanged during that redox reaction? In which case, you would indicate chlorine. You'd click chlorine. All right, let's do another one from scratch and start getting good at this. I'm going to draw cards on this one. Be ready. All right, let's go over to cluster 1, seat 6. Hey, 1-6, you're nice and close. This is a single replacement or redox reaction. How do I know that?
Because it's a compound and a free element.
Compound and a free element, all right? Don't do synthesis stuff. Don't do decomposition stuff. Realize, what the heck am I looking at? Single replacement, redox. Then you think through activity series and pluses and minuses, because only redox does that. Keep them separate. All right? So let's find like charges. Remember, the way that I know what's going to swap is by general charges. Let's go over to cluster 6, seat 6. No, there is no 6-6. You're 6'4". He's 6'5". Aspen, where are you? Hey, Aspen, help me out. What is this potassium's general charge, positive or negative? Yeah, he's generally positive. What about bromine, if you want to keep helping me? Generally negative. And what about chlorine? Generally negative. Everybody okay with the red? All right. So then who wants to swap? Well, it's the ones with like charges. So the bromine and the chlorine want to swap, but you can never assume that it's definitely going to happen. Instead, we look at the activity series. Oh, but looky, I got to show you something. I want you to look in the very top corner. Look in the very top corner, and you'll see there's a little baby activity series up there for the halogens. All right, so you've got your long list here, and you've got a little list up here for halogens. But it works the exact same way. The reaction only happens if the free element is higher on the list than the element it wants to swap with. Anybody in the room? Is chlorine above bromine? Yes, so it's going to happen. Let's do it. Switch them. Bromine's going to come over here and be by himself. Chlorine's going to come over here and marry potassium. Does it matter the order you write the products in? No, it's an addition problem. 1 plus 2 is the same as 2 plus 1. Landon hasn't yelled at me yet, but he wants to. Check what you wrote. Bromine is a free element, so drop a deuce. Compound, it's ionic metal to non-metal, but it's +1, -1, so there's nothing to do to him. Right, it looks like it's going to be a 2 to 1 to 1 to 2 mole ratio if you are a sharp little balancer. Questions so far? So we predicted the products. This is what would happen in nature if these two dudes were to come into contact with each other. But what if we wanted to do a redox analysis? What if we cared about electron movement? Here we go. Make a list. We got K, BRs, CLs. I'm going to pick on someone to give me all of the reactant charges. Be ready. Let's see if it's you. Let's go to cluster 4 and talk to seat 2. Hey, 4-2. What is that potassium's exact charge? +1 is perfect. What is this bromine's exact charge? -1 is perfect. And what is this chlorine's exact charge? So wonderfully beautiful. Does anybody have any questions about those three numbers? On the other side, we do the same thing. Bromine is a free element. Free elements are always 0. Bonded potassium, +1 from group 1. Bonded chlorine, -1 from group 17. Now, I want to show you something. Some students really struggle with oxidized versus reduced. You just have trouble with vocab. So we can go all 6th grade on this if you want to. There's a number line here. I'm not telling you to write it down, but you can. But look at bromine. You see how bromine starts at -1 and goes to 0? If you were to have this image and you were to put your finger on -1 where bromine starts and slide it over to 0 where bromine ends, you would have slid this direction, which matches up with oxidation and loss of electrons. It's a little cheaty way to graphic organize it in your head. So if you know that you're better with this kind of stuff, fine, but I'm not giving you a number line on the exam. But whatever, I don't want to not offer another way to look at it. Yeah. Yes, the activity series will be given to you. So yeah, so we just said he was oxidized. Really, the way I want you to think about it is to say bromine became more positive. To be more positive is to lose electrons, which by definition is oxidation. All right, we can see that potassium didn't do anything with his electrons. Chlorine became more negative, gained electrons. That is being Let's do 2 more, but these are going to go a lot faster. Don't cheer all loud. Let's look at our 3rd example. I know it's single replacement because it's a free element reacting with the compound, so I look for general charges. Metals are always cations. Lithium is a cation. And yep, hydroxide's a polyatomic, but just look them up. Hydroxide is an anion. I'm going to draw a card. I want to know, will the reaction happen? Look at what's what. Will the reaction happen? I'm going to go over to cluster number 2 and talk to C2. Hey, 2-2, do you think it'll happen? The answer is yes. Do you agree?
Yes.
It's not going to happen. It ain't going to happen, y'all.
Oh.
The element by itself must be higher on the list than the one it wants to swap with. Look at the 2 pluses.
I got it mixed up.
Iron would have to be higher than lithium, and if you look, nothing is higher than lithium. Lithium's at the very top, all right? Y'all, it's really good news when it's a no reaction because then you get to do this and you're done. There is nothing to do if nothing happens. Don't.
Terrible.
What do y'all think about this? Can you do one by yourself? All right, so hey, my last example of the day is about to pop up. If it's a no reaction, then figure it out and just stop here. Maybe it's a no reaction. If there is a reaction, then I need you to do everything that we've done today, all right, all the way through oxidized or reduced. So figure out where it is, and then take the 5 minutes and get it done. Good luck.
For these? I think the first one. Or we're talking about over here. Okay. How do we do that?
What'd you get? Yeah. H2 plus HBI. Yeah, I just did it the other way. That is better. I kind of saw it coming too, and I was like,
No.
after the game, it was like, that was a yellow card. I was like, oh. She said, was that a yellow? Yeah, it was a yellow. And then the Megan parents were talking about. They were. They say.
Nathan. How about?
Dude, that's not for Brexit.
Okay, for these? Yeah, how do I lay out?
Okay, so for the hydrogen, it became a little element, so it's gonna be 0. The iodine, it stayed in a compound, so it has a -1 charge, so nothing happened. The magnesium actually so it has the regular charge, so.
Yeah, I can't let you. If you take AP, I'll let you do it, but otherwise you're gonna break your finger. Does this look cool on camera? Oh, not like that. I want to see the slow motion. Just slow mo, fine.
I didn't get off of Monopoly Go.
Are we done here?
Hold on, chill out, chill out. All right. Hey, if I do something you don't understand, stop me right away. I know it's a redox reaction because one of those is a compound and the other's a free element. That's the most important step. Here, quit putting your stuff. You got time. Quit putting stuff away. All right. Here's my general charges based on location on the periodic table: plus, negative, plus. Therefore, the hydrogen and the magnesium want to swap. However, they'll only switch if the magnesium's higher, the free element, than the hydrogen. Is it?
Yes.
It is. Yep, magnesium's higher than hydrogen. So I'm going to switch the pluses. When I do that, hydrogen is now by itself, and he's diatomic. And now the magnesium joins iodine. And when you check the charges there, magnesium's oxidation state of 2 will cross. Iodine's -1 does nothing. All right, and then you can... Redox analysis goes hemig. A bonded hydrogen is +1. A bonded iodine is -1. Those are their normal predicted charges. But a free element, anything, is 0. A free element hydrogen is 0. A bonded magnesium is +2. And a bonded iodine is -1. Hydrogen is gaining electrons, becoming more negative. He's reduced. Iodine does not change his electrons. Magnesium is losing electrons. He's becoming more positive. How did y'all do?
Good.
Yes, we did.
Yeah, we got it.
There's only one reaction type left.